In this video, we're going through the basic of conservation of energy. Now, the definition for principle of conservation of energy states that energy cannot be created or destroyed. Rather, it can be converted from one form to another or transferred from one body to another. But the total energy remains constant in the closed system. Over here, we have three examples. The first one here is like a roller coaster kind of question where the ball is released from rest going down an undulating track. And second scenario here, we have a ball released from rest and it falls towards the earth. And the third one being a pendulum bob here, it swings from rest going down and then goes to sea and it keep on oscillating. For a start, let's assume that there's no air resistance as the ball falls or there's no friction along the track. So based on conservation of energy, that means to say at any point along the movement, the total energy of the ball remains constant. So the total energy of the ball here, B here or D here will be the same. Okay, likewise for the pendulum. So how do we find the energy of the ball? And for these three scenarios, we'll be looking at the ball at position A because it's released from rest. So initially it doesn't have a speed, it doesn't have a KE. And because we're given the height of the ball, we know the GPE, the gravitational potential energy, and that is the energy the ball possesses. So that will be the energy of the ball and it will be the same throughout. So how do we find the total energy? Let it be ET, total energy. And because the total energy at any point A, B, C or D will be the same. So that means to say the total energy at point A is equals to total energy at point B to point C and is equals to the total energy at point D. So the total energy remains constant. And to find the total energy of the ball, we have to make use of the position A because as mentioned at position A, the only energy it has is GPE because it has a height of 10 meters above the ground, and because it's released from rest, there's no KE. So it's very straightforward, allowing us to find the total energy, which is just gravitational potential energy, mgh. The mass is 2 kg times gravitational field strength on Earth is 10 and the height is 10. So we have the total energy 200 joules. That means to say the energy of the ball here is 200 joules. As it goes down the track, at point B, the total energy will be 200 over here, and at point D is also 200. But the difference is between the highest and the lowest reference ground here, as long as the ball is in between, so it will have a combination of GPE because of its height, and because it's moving, it will have KE. But if you total up the total energy, it will always be constant 200. Likewise for point C, which will be 200 joules. But of course, at point C, due to its higher height, the GPE will be higher compared to the at point B. And for point D, because the ball is at the reference ground, there's no height, no GPE, so all the energy will be KE, which is 200 joules. So you can see that at the lowest point, the KE will be the maximum because most of the energy will be converted to kinetic energy. And the same goes to the other two examples. As you drop the ball from A, as it goes down, the GPE decreases, the K increases, and just before impact on the ground at point D, that will be the maximum kinetic energy, maximum speed. And likewise for the pendulum bob, at the lowest point at point D, where there's the reference ground, the KE will be the highest and the speed will be the highest. Next, let's focus on calculation question based on conservation of energy, and we are going to find the speed of the ball at point D and also at point B. So we'll be focusing on this example because the concept is the same for the other two. Let's start with finding the speed at point D. As mentioned, because total energy remains the same, so I'll be finding the total energy at point A equates to total energy at point D. But why A? Because at point A, it allows you to find the total energy of the system, because over here there's no KE and we are able to find the GPE, which we already found here, which is 200. So nonetheless, I'll still write here, but I want you to follow this format because it's very systematic. So when you solve, you always write the KE at point A plus GPE at point A, because that will constantly remind you whether to check whether there's KE or GPE at a different position. Likewise, KE at point D plus GPE at point D. So now then you check at point A, because it's released from rest, there's no KE, no speed, so I'll cancel. And at point D, because it's at its reference ground, no height, no GP, so you're left with the mgh at height A equals to half mv squared for the speed at point D. So then you sub in the value, which is the mass 2 times gravitational field strength 10, and the height at A is 10. So it's half times 2 times the speed of the ball at point D. Do not forget the square here. And if you solve it, you will find that the speed will be 14.1 meter per second. Now, there's another advantage of presenting your working this way is when they ask you, does the speed of the ball at point D depends on the mass of the ball, which is 2 kg. And for this scenario where there's no air resistance, no friction, the answer is no. So the speed of the ball, not just at point D, but rather at any point, is independent of the mass. And how do you show or prove it? Is from here. So if we were to simplify here, and you can see that mass is a common term, that's why I can actually cancel away. So the speed at point D, if you manipulate the formula, is 2gh square root. So as you can see, the speed, and inside here there's no mass component. In other words, the speed of the ball at any point is independent of the mass, provided this situation where the friction and air resistance is considered negligible. Next, let's find the speed of the ball at point B. Before you start doing, you should know that the speed at point D will be lower than the speed of the ball at point D, because at point D low is lower, so the speed should be higher. So we'll be using the same techniques. I'll be using the total energy at point A, equate it to be the same as the total energy at point B. Now, of course, you can choose any 2 points. I can also choose total energy at point B equals to total energy at point D, because I already know the KE, the speed of the ball at point D. But what if this answer is wrong? So that will lead to another wrong answer. So theoretically, you can use any 2 points. So I will still stick to A because that's the easiest, and I already know it's 200 here. So from the previous part, you know that there's only GPE and it's 200. And then for total energy at point B, it will have a combination of GPE and KE. So 200 equals to mgh at point B plus half mv squared at point B. So you sub in the value, 2 times 10 times the height at point B is 2 meters, plus half times 2 times the unknown speed that you want to find. And just if you solve it, the answer will be 12.6 meter per second. And indeed, this speed here at point B is lower than the speed at point D. So with these 2 examples here, I hope you are able to apply conservation of energy to find the unknown that is required by the question. Now, what if the question gives you a more realistic setting where there's friction, and let's assume that for every 1 meter, there's an average frictional force of 2 meter experienced by the ball, and the whole track is 50 meter. That means as the ball goes down the track from A to D, some energy will be converted to work done against the friction. Of course, it will result in the form of thermal energy and sound. So how do you solve that kind of question? Now, we will still be using conservation of energy, and let's say over here, total energy at point A equals to total energy at point D. So it will be the same whether there's friction or no friction. Conservation of energy will always apply. And we already know that at point A, the only energy it has is GPE at point A. And of course, if there's no friction, all the energy will be converted to KE at point D. But because there is friction, and for every meter, there's an average frictional force of 2 newtons. So the work done against friction will be the force times distance, which is 2 times the total length of the track, 50. That will be 100 joules. So in other words, this 100 joules will be wasted in the form of heat and sound. So I have to add in the component on the right hand side, work done against friction. But some of you may prefer to see it this way. So you can also write it this way: the original energy minus of away the work done against friction, and that will be the remainder will be for the KE at position D. So depends on which presentation you are more comfortable with and you understand better, you can write both are the same. So you will know that the KE at point D will be lower than just now because of the frictional force experience, and the speed of the ball at point D will definitely be lower than 14.1. You can do the calculation. So that's how you solve it.